Welcome to lecture number 4. Today we are going to discuss atomic orbitals as well as hybridization. One thing that I do a little bit differently than some college professors is I personally do not teach molecular orbital or MO theory for entry-level organic. Personally, I believe that MO theory is unnecessary for the topics that we will be examining. It does help to supplement some topics later on and better explain certain things. However, for its level of complexity, I believe that it's best left out for introductory organic. So if you do happen to have a test specifically on molecular orbital theory, I apologize, this video may not be the most useful to you. But I believe that understanding organic chemistry, understanding why things happen and why they happen the way that they do, can be done in entry-level organic simply through atomic orbital theory. Okay. So let's hop right into atomic orbital theory and hybridization. Some of this should be reviewed from general chemistry or high school chemistry. We should be aware that there are atomic orbitals or areas where we could have electron density, right? And these orbitals go from the s orbitals through to the p, d, f, and beyond. Luckily for organic chemistry, we are really just going to be focused on the s orbitals and the p orbitals. Okay. We will use some elements from the D block, some metals, etc. But in terms of considering its electrons, its valence electrons, we don't have to get into that. Okay. So let's recall what these orbitals look like. Remember, the s orbitals are simply spheres. So this would be the 1s, the first atomic orbital, lowest in energy orbital. The 1s orbital is just a sphere of space around some atom where electrons could exist. The 2s orbital, in the same way, is just another sphere, a little bit further from the nucleus, a little bit larger, where electrons could exist. And then we have the p orbitals. And these p orbitals are shaped like dumbbells, and they run along the axes of a Cartesian coordinate, XYZ coordinate. Okay, so we could have these p orbitals along the x-axis, along the y-axis, or along the z-axis. So there's 3 p orbitals. Sometimes you'll see 2px, 2py, and 2pz, or you could just see 2p, 2p, 2p. Sometimes they're denoted xyz. Either way, remember there are 3 p orbitals. Okay, 1, 2, 3. And let's draw their shape here. So let's denote this as the x-axis. We have sort of a dumbbell shape along one axis there. Sort of a dumbbell shape along the y-axis and along the z-axis. So those are the p orbitals. They're dumbbell shapes where the atom is at the center of a Cartesian coordinate. So there's 3 p orbitals like this. Okay, this will be important for today's lecture. Okay, at some point in your past, you probably should have also set up an electron diagram. Now, I'm going to draw this arrow on the side along with a capital E for energy, meaning that as we go up in our diagram, we are increasing in energy. So we're going to put the lowest energy orbital at the bottom. Okay. So let me fill in these atomic orbitals. We'll start with the 1s orbital. The 2s is above that. And then we have 3 orbitals for the p, 2p. And these 3 orbitals we would call degenerate orbitals. Degenerate orbitals meaning they are same energy. Okay, so that's a term you'll hear me use. That's a term you'll see is degenerate orbital. That means that any orbitals that are degenerate are same in energy. So the 2p orbital, the 2p is made up of 3 degenerate orbitals, 2px, 2py, 2pz. Let's write that in here. We have our 2p's, we have our 2s, and we have our 1s. Now let's fill this electron diagram in for nitrogen, okay? Let's fill this in for nitrogen. Now remember, when you fill these electron diagrams in, you have to follow these 3 rules: Aufbau principle, Pauli exclusion principle, and Hund's rule. Okay? Hopefully you remember what these are. Aufbau principle. This simply means that you start with the lowest energy orbital first. Okay? You simply start by filling the lowest energy orbital first. Okay, and then there's the Pauli exclusion principle. This principle states that you can only have 2 electrons per orbital, and they should have opposite spin. Okay, so let's put that here. 2 electrons per orbital with opposite spin. Spin is something we don't really have to think about for this class, but you should just be aware of the fact that electrons, when they are paired up, like to have opposite spin. Okay, we don't have to go any further for this class. Okay, so Pauli exclusion principle means that we should have 2 electrons per orbital with opposite spin. And then Hund's rule states that we should fill degenerate orbitals one at a time. So looking back at our example here, our 2p orbital has 3 degenerate orbitals. We should fill these up one at a time. If we have maybe 4 or 5 or 6 electrons to fill these orbitals with, we fill the x, we fill the x with 1, we fill the y with 1, we fill the z with 1, and then we go back to the x. We don't pair up electrons first, okay? First we fill the orbitals, and then we pair them up. So let's write that here. First, fill degenerate orbitals, and then pair electrons. That's my abbreviated definition for you. Okay, first you fill up degenerate orbitals, you fill them with 1 electron, and then you go back and you pair them up. Once you see this in action once, it's easy to remember. Okay, so let's fill up electrons for nitrogen, okay? Now, what we have to do here is we have to consider nitrogen on the periodic table to remember how many electrons we have, okay? So you can refer to a periodic table. Nitrogen is 7, okay? Nitrogen is number 7, which means it has 7 protons and 7 electrons when it's neutral, okay? So if we want to fill this diagram in for nitrogen, let's fill this in with 7 electrons, okay? Let's first fill in the 1s orbital with 2 electrons. Each electron is indicated by this single-headed arrow. Okay, one is up, one is down, indicating their spin, opposite spin, up and down. There's 2 electrons, and then 3, 4 electrons. And then remember, following Hund's rule, we do 1 at a time here. So we have 3 electrons left. 1, 2, 3. If we had more, we would add 4, 5, 6, like that. Okay, but we just have 7 electrons total, which means we're left with 3 orbitals, or 3 electrons for our 2p's. Okay, so that gives us one electron in each of the two p orbitals. So this is the electron diagram for nitrogen. Now, it's interesting to look at this because it sort of explains why nitrogen is the way that it is, right? We see in our valence shell here, we have 5 electrons. We have a lone pair and 3 single electrons. If you recall what nitrogen looks like, we have a lone pair with 3 single electrons. Those 3 electrons are where we can make chemical bonds, right? So we have a lone pair and then 3 bonds, and we can understand that by looking at the electron diagram. So organic chemistry is all about the movement of these valence electrons. It's all about these valence electrons either reforming, hybridizing, making new bonds, joining a new atom or bond, or simply leaving. Okay, these electrons can do all sorts of things, and this is going to dictate what happens in organic chemistry. So the valence electrons are very important. Okay. Okay, so now that we have some basic information down, let's quickly ask ourselves the question, what actually is a bond? How do we get a bond? And where are these electrons? Okay, then we'll hop back into the orbital diagrams and consider some other atoms. But first, let's just take a step to the side here and ask ourselves, what exactly is a bond? So let's think here. Let's look at just hydrogen. Remember, hydrogen just has one s electron. It's a 1s1. Hydrogen atom is just composed of a proton and an electron. So hydrogen has one electron, and we could make a hydrogen molecule, H2, by combining 2 hydrogens. Now, both of these electrons are in a 1s orbital around hydrogen, right? So let me draw the product here of a bond between 2 atoms of hydrogen. That would give us H2. Now, this electron here, these electrons around hydrogen, they aren't just sitting off to the side as we've drawn, right? Those electrons don't just sit there. And a hydrogen atom doesn't actually look like an H. Remember, we're just representing, atoms, we're representing subatomic particles with letters and pictures, right? So yes, there's just a dot next to an H. This isn't what it looks like though. Remember, in actuality, this electron can be anywhere around this H in the 1s orbital, right? That electron can exist anywhere in that 1s orbital around the nucleus or around that proton of hydrogen. Okay, so we have sort of this bubble of electron density around hydrogen. And again, if we have another hydrogen atom, we have the same bubble around hydrogen. So when they make a chemical bond, these two bubbles sort of overlap, okay? Again, this is the 1s orbital, this is the 1s orbital. And when these two make a bond, these two spheres sort of overlap like this. Okay, now I'm not a great artist, but it's almost like when two bubbles, if you're blowing bubbles as a kid, and two bubbles collide with each other and they become fused for a second. That's almost what it looks like. These two bubbles of electron density sort of fuse together. Okay. And when these two bubbles fuse together, then we have a pair of electrons that can exist anywhere in this bubble. But typically, those electrons exist between the two hydrogen atoms most of the time, okay? But again, if there is influence from, if this is on a larger molecule, those electrons can be influenced, remember, through polarity, through some intermolecular forces that we'll talk about next lecture. And those electrons can shift around, okay? Typically, though, they are between the two atoms that they're bonding, in this case, between the hydrogens. But what we have to understand here is a key concept that overlapping orbitals creates bonds. Overlapping orbitals creates bonds. So we have this 1s orbital, we have this 1s orbital on these two hydrogen atoms, and they come together and they overlap to create a chemical bond. I'll draw it over here again. We have this 1s orbital, and then I'm going to draw another H with another 1s orbital. They overlap and they create this shared connection, this chemical bond. Okay. What we call this right here is a sigma bond. This is called a sigma bond. When you have a single bond between two atoms, this is called a sigma bond. This is the symbol for sigma. So you might see that written out. A sigma bond. A sigma bond, again, it's just your basic single chemical bond between two atoms. So we could, on the left here, I'm going to draw something here. I'm going to draw a molecule of ethane, a Lewis structure, so we can see all the bonds. All of these bonds in here are sigma bonds. Okay, your sigma bonds is just your typical run-of-the-mill chemical bond. And they are created from overlapping orbitals. Okay. Okay, so using all that information that we have so far, let's introduce a little problem we have. Okay. So this problem, let's see, is with carbon. Okay, it starts with carbon. Let's consider carbon's Lewis dot structure. We have a C with 4 bonds around it. We could make CH4, for example, using carbons and hydrogens, just a simple tetrahedral structure here, carbon with 4 hydrogens. Now, let's first fill in the electron diagram for carbon. Okay, let's fill that in. Now, carbon should have 6 electrons because it's number 6 on the periodic table. So a neutral carbon atom should have 6 protons and 6 electrons. Let's fill this diagram in. 1, 2, 3, 4, 5, 6. Okay, so you see this doesn't look as pretty as nitrogen. Nitrogen, it sort of made sense because we had a lone pair with 3 single electrons, and that's exactly what the Lewis structure looked like. But for carbon, it doesn't look like that. It says we have a lone pair. Let me draw the orbitals in. This is the 1s, the 2s, and the 2p's. Our valence shell, the 2s and the 2p, says we have a lone pair and 2 single bonds. That doesn't make any sense because carbon, right, it should have 4 atoms, 4 electrons, just like this. And when we do chemical tests, all of these CH bonds here, all of these are chemically equivalent. They are all equal. So we have a discrepancy here. Our chemical tests are showing that all of these CH bonds are the same. They're equal. There's no difference. But our electron diagram says we have 2 p electrons and we have 2 s electrons, different energy levels, different energies. Something's not making sense here. Okay. So this is not how we would draw the chemicals, the electron diagram for carbon. We would actually draw this one over here on the right, and we are going to draw it using a hybridization technique where we hybridize these orbitals. Okay, so how that looks is our 1s orbital stays untouched. Okay, 1s orbital stays untouched, but the 2s and the 2p electrons will combine. They'll combine. Get the line tool here, and let's draw 1, 2, 3, 4 orbitals, all equal in energy. And the name for this orbital is going to be the sp3, because these orbitals are composed of 1s orbital and 3p orbitals. So let's call these the sp3 orbitals. So these p orbitals, again, these p orbitals over here on the left, and this s orbital, the 2s and the 2p, these atomic orbitals combined, mixed together to make 4 degenerate orbitals known as sp3 orbitals, because we have 1 s and we have 3 p's, all combining together to make these 4 orbitals. If you mix 4 orbitals, you get 4 orbitals. If you mix 3 orbitals, you get 3 orbitals, etc. Okay? So we mixed our 2p's, we mixed our 2s's, we made these sp3's, okay? And now let's fill in carbon's electron diagram. 1, 2, 3, 4, 5, and 6. Okay. So now we have a much better representation for carbon, where we have 2 electrons in the 1s shell, and now we have 4 electrons in the sp3 hybridized orbital around carbon, where these 4 electrons are all equal and can participate in chemical bonding. So this explains why carbon has 4 bonds, right? This helps us explain how these valence electrons look and why carbon has 4 single electrons, which can all participate in bonding. Okay? It's because of hybridization. It's because of hybridization. Let me draw a definition for hybridization here. Let me write it out. So when we consider hybridization, this is the combining of atomic orbitals to create an equal number of new mixed orbitals. Okay, so there's our definition. The combining of atomic orbitals to create an equal number of new mixed orbitals. So in the case of carbon, we combined our 3 2p's and our 1 2s to make 4 sp3 orbitals here. Okay, hopefully you can see that. We combine those on the left in the circle to make these 4 on the right in the circle. Now, what does an sp3 orbital look like? Well, if a s orbital is a sphere and a p orbital is a dumbbell shape, then an sp3 orbital, if we combine 1 of these and 3 of these, it's just an averaging of these. So it'd mostly look like the P, but there'd be a little bit of S influence in there too. So what it ends up looking like is you just have sort of a slightly lopsided p orbital, where one orb is a little bit larger. So this would be sort of the appearance of an sp3 orbital, how you may see it represented, okay? But you don't really have to be too considerate about its shape, okay? Unless perhaps your professor asks specifically for you to draw the shape of an sp3 orbital. This is what it would look like. It'd be a lopsided p orbital, but it would mostly look like a p orbital because you have 3 of them and then just one s orbital. Okay, so that's the shape. Now, if we were to draw the shape, making an overlapping chemical bond, we could do that too. So if the sp3 orbital looks like that and you have a carbon atom making a bond to a hydrogen, okay, the sp3 orbital would look like this, a lopsided dumbbell. Maybe you have a CH bond here, and it's overlapping here. Okay, so this would be a CH bond. We're making a bond between the s orbital, the 1s orbital of the H, and the sp3 orbital of the carbon. Okay. So again, if we make a CH bond, if we were to draw it out, it would look like this, where we have this sp3 orbital, this big lopsided dumbbell, overlapping with the 1s orbital of a hydrogen atom. Remember, a hydrogen atom only has a 1s orbital, so if it makes a bond, that means its only orbital, the 1s, is just overlapping with another orbital. You don't need the orbitals to be the same to overlap. You don't need a 1s to overlap with a 1s, right? Any orbitals can overlap as long as the geometry allows them to. So in this case, we have an sp3 orbital overlapping with a 1s orbital. Okay. So again, carbon will hybridize to create this atomic orbital system here, where we have a 1s orbital, and then we have these 4 degenerate sp3 orbitals. So this is carbon with 4 single bonds. Okay. This is how you'll typically see carbon. Okay, so as is tradition in organic chemistry, now that we learned something, we are going to sort of change it and break it even a little more. So this is for carbon with single bonds, but what happens when carbon has a double bond or a triple bond, right? We don't have 4 single electrons that make 4 equivalent bonds at that point. Something else happens. Okay, so let's take a look at that now. Okay, so now we have a C double bond C. And just quickly, so we know the terminology here, we can call double bonds many things. We can call them double bonds, olefins, or sometimes you just refer them, but you'll see them referred to as enes, because this is the suffix that you add to double bond systems. Okay, you could also hear them as being unsaturated, right? If you have units of unsaturation, that could be another term you hear for double bonds. Typically, though, we'll just hear them called either double bonds or olefins. Okay, so when we have this CC double bond, our electron diagram that we just made before no longer makes any sense. Let's again look at carbon's expected diagram, how we would draw it if this was high school chemistry. We would go 1, 2, 3, 4, 5, 6. Okay. Now, in the case of a C-C double bond, we actually get hybridization of these 3 orbitals, but we exclude one of the 2 p orbitals. We exclude one of them, and it should be clear to you why as we get through this section here, okay? But let's just go ahead and draw a new diagram here where we hybridize these three orbitals. They'll go a little bit lower in energy than the 2p because we're pulling an s into the mix here. So let me draw these in. We have our 1s orbital, which is exactly the same. This is untouched. And now we're hybridizing a 2s orbital and two 2p orbitals. So if we hybridize 1s with 2p's, we would get we would get sp2. Let me try that again. sp2. Okay, we get our sp2 hybridized degenerate orbitals. And then our 2p orbital up here, whether it's the x, y, z, it doesn't matter. Our last 2p orbital is left untouched. Maybe I'll highlight the ones that are untouched in red. This orbital here is untouched, exactly the same. And this 2p orbital is untouched, exactly the same. We are mixing the orbitals in black, the 2s and 2p's, to create the sp2 hybridized orbitals. Okay, let's go ahead and fill this structure in now. Let's fill this diagram in now. 1, 2, 3, 4, 5, 6. We actually include an electron up in the 2p orbital as well. Okay, you can think of these as being degenerate. Okay, so we have these sp2 orbitals, 1, 2, 3, and then we have this 2p orbital. I'm going to draw ethylene at a little different angle here so that we can sort of take a look at what's going on. So we have this CC bond, and I'm going to draw this molecule in such a way that we can sort of get an understanding of how it looks. Ethylene is a flat molecule. It's flat. So you can envision this as sort of resting on a table or a piece of paper. All of the atoms in ethylene are in the same plane. It's two-dimensional. We'll talk about that in a second as well. Now the CC double bond, this is what's important here, okay? The CC double bond is not a sigma bond, but this is a pi bond, okay? This is a pi bond. Sometimes you'll see it using the symbol pi or just pi. And the single bond is still a sigma bond. So there's still a sigma bond, but there's also a pi bond in the case of double bonds, okay? So a double bond is composed of one pi bond and one sigma bond. Now the pi bond is a overlapping of p orbitals, okay? This is important. Pi bonding is an overlapping of p orbitals. Overlapping of p orbitals. Okay, so these pi bonds have to be made using p orbital electrons. Let's look back at our electron diagram. We have this 2p electron right here. This is the 2p, this is the electron in the p orbital that's making that pi bond. Okay, so let's draw this p orbital here. We have an electron up here in the 2p. Likewise, we have an electron here in the 2p, and they are making a bond together. They are making that pi bond, that double bond between each other. Okay, so this is the pi bond here. It's the overlapping of these p orbitals. Here's the sigma bond, which is simply the overlapping of the sp2 orbitals. The pi bond is the overlapping of the p orbitals. So this is where it can get confusing, and I understand that. So let me explain everything again, sort of a different way. We're looking here at ethylene. Okay, ethylene. The electron diagram for ethylene, what we do is we hybridize one orbital, the 2s orbital, with two 2p orbitals, the ones that are circled here. These orbitals combine together through hybridization, mix together to give us these orbitals over here, the sp2 orbitals. And we also have this 2p orbital left over. We leave a 2p orbital because we need to make a pi bond. We need to make that pi bond. We need to explain why that pi bond exists. And pi bonds exist from overlapping p orbitals. So we can't use all of our p orbitals up for hybridization. We need to leave one to make that pi bond. We have to leave one there to make that pi bond. Okay. So we're going to leave a p orbital for the pi bond. The other orbitals in the 2 energy level will be hybridized together to make these sp2 orbitals. So if we look back at our molecule here, I'm going to draw it up top now. All of these bonds here are no longer sp3 hybridized. These are sp2 orbitals. These are sp2. All these bonds here to carbon, sp2, 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 right? So the bond between the 2 carbons is overlapping sp2 orbitals. But all of these are sp2 hybridized bonds coming from carbon. Now remember, hydrogen can only make bonds with 1s orbital, so all those are 1s. But all the bonds coming out from carbon are coming out in what we would call the sp2 orbital. Why? Because one of the p orbitals is making a pi bond. Let's draw it in blue. One of the p orbitals is responsible for making this pi bond here, and that's this electron in the 2p orbital. Okay, so this is overlapping of the 2p orbital. Okay, this pi bond, which is an overlapping of p orbitals, is being made from the overlapping of this 2p orbital on one carbon and a 2p orbital on another carbon. Okay, so it can get pretty complicated, it can get pretty confusing, but hopefully as we continue the lecture, as we look at our last example here, hopefully it becomes a little bit more clear. Okay, but I do understand that this is sort of a point of contention for a lot of students, and I will just say now, it's not the most important information to remember all this. This just helps explain reactivity, helps explain why things are the way that they are. We'll summarize everything at the end. So if your head's spinning right now, that's okay. Okay. At the very end, we'll summarize everything, hopefully in a nice, concise way, and really just pull out the details that we really need to know. Okay. What we should definitely remember from this section here is that when a carbon has a double bond, it's sp2 hybridized. Okay, so at least remember that. If we can remember that, that's good. When we have a CC double bond, that's sp2 hybridized. Okay, that's sp2 hybridized. Why is it sp2 and not sp3? Because the last p, remember we have 3 p's, that last p is being used for the double bond. This double bond here. This last p is being used for the double bond. Okay, that's sort of a summary right there of this slide. But again, at the end of the lecture, we'll go through and sort of summarize everything. Okay. Okay, so now let's look at the CC triple bond, which is the last way that we could see bonds to carbon. And again, we're spending so much time on carbon because that's really what organic chemistry is, right? Most of the atoms we look at will be carbon. Organic chemistry is essentially the study of carbon-containing compounds. So carbon is very important to us in organic chemistry. So let's look at this triple bond. We could also see triple bonds being called ines or alkynes, double bonds, alkenes, triple bonds, alkynes. Alk just means carbon containing. Yne, Y-N-E, means triple. If you see E-N-E, alkene, that means double. Alkane, A-N-E, just means single bonds. Okay. We'll spend some time at a future chapter sometime soon with nomenclature, but just in case I use some of these words subconsciously, you know what I'm talking about. Okay, so looking at this triple bond, we have carbon triple bonded to carbon. We have a hydrogen on either side. So the first thing to consider is the typical diagram. Let's fill that in over here, 1s, 2s, 2p. And again, that doesn't make any sense, right? This doesn't make any sense. So hybridization must be occurring here. Okay. So how do we hybridize these atoms? How do we hybridize these orbitals so that this bonding pattern makes sense to us? If we have two pi bonds now, let's draw the pi bonds with blue. Remember, the sigma bonds are the single bonds connecting everything. Once you get to double bonds and triple bonds, those extra bonds become pi bonds. Pi bonds. And now that we know pi bonds are overlapping p orbitals, how many p orbitals should we leave? We should leave 2 p orbitals. So let's hybridize and mix a 2s orbital and a 2p orbital. That's going to give us this sort of structure here for our diagram, where we have a 1s orbital followed by our sp hybridized orbitals, because we're taking 1s and 1p. We're taking the 2s orbital and the 2p, one of each, to give us sp. And then we have our remaining 2p orbitals, which again, I'll draw in blue here because these will be responsible for our pi bonds, the double and triple bond that we're making. Okay. Let's fill this in. We have 1, 2, 3, 4, 5, 6. Okay. Now these orbitals, it might be confusing that we're not pairing up these electrons, even though they're not drawn, they're drawn at different energy levels. Okay. We pair them up because we consider them degenerate. We're just drawing them in different sections. Okay. These really are very similar in energy. Okay. Don't let that confuse you. So now we have 2 electrons in the 2p orbital because we're making a double and triple bond, so that makes sense. And then we have 2 electrons that are in this orbital known as the sp. And the sp orbital, that's the bonds up here in black between the carbon and the carbon, from the carbon to the hydrogen, and from the carbon to the hydrogen. Okay, so this carbon, if we look at this carbon right here, this carbon is making bonds using an sp orbital in this direction, an sp orbital in this direction, and then it's making double and triple bonds up here with its p orbitals. Okay, there's the p and there's the p. So there's all of our orbitals. 2 of the p orbitals, the untouched orbitals here in blue, are responsible for the pi bonds, the double and triple bond there. The remaining orbitals, sp, those are combined to create two degenerate orbitals where carbon is making two quote unquote normal bonds. Okay, so carbon, when it has a triple bond to it, is sp hybridized. It makes two normal bonds, two sigma bonds, and then it has two pi bonds. Okay. Now, a triple bond carbon, a C triple bond C, for example, is linear. Why is it linear? Well, it's connected to two things. It's connected to one thing on the right, say it's a hydrogen here, and say it's connected to a carbon here. This C triple bond C is linear. This is a linear molecule. There's not really any three-dimensionality to it. Okay? It's only connected to two things, so it's very similar to our previous example in the last lecture of beryllium hydride, where this beryllium is connected to only two things, right? If something is only connected to two things, you can understand how that molecule is a straight chain molecule, where the two functional groups are 180 degrees apart. Those two bonds are on opposite sides of the carbon to give us a linear structure. Okay, so carbon with a triple bond is linear. It's sp hybridized. Two of its p orbitals are left behind to make this double and triple bond. Okay, maybe I can represent that with some three-dimensionality here. Okay, we have carbon bonded to carbon. I'm going to draw it nice and long here. Let's put a hydrogen on either end. So these bonds in black, these are sp bonds coming from carbon, sp. Now the p orbitals here, we have a p orbital coming up like this. And for triple bonds, we have p orbitals also coming out at an orthogonal angle. So this could be the px and the py, right? Or the pz and the px, whatever is orthogonal to each other, given the structure here. And if we have one electron, let's do this maybe in blue still, do all of our pi work in blue. Okay, let's look at these two orbitals in blue. These are overlapping, one electron in each one, to create a pi bond. And then let's maybe do in a darker blue here, this other one. This other p orbital is also overlapping, one electron in each one, connecting to make the triple bond. Okay, so we have one p orbital going up and down, overlapping to make a bond, a pi bond, and then we have another p orbital which is orthogonal to it, also overlapping to create a pi bond. So ultimately we have, if we can count the bonds here in the middle, if you can see my cursor, we have this light blue bond here, we have this black bond, and we have this dark blue bond here. So we have 1, 2, 3, we have this triple bond between these two carbons. Okay, again, I understand this section here was a little tricky, perhaps a little bit difficult to understand, but let's take a second to sort of summarize everything and just extract out the most important pieces of information that you need. Okay, so let's summarize our single, double, and triple bonds to carbon here, and just pull out the important pieces of information that we need to know. If the electron diagrams confused you, that's okay. It also confused me when I first learned about it. But once you get to work with these hybridizations, for a while, and then you go back to the diagrams at a future date, it should make more sense to you. Okay. But again, if you're just trying to get through organic chemistry, this is the stuff that you'll need to know right here. So I have the hybridization and the geometry, which we'll talk about. I also put down at the bottom the bond length and the bond energy, just as little extra bits of information. In fact, I'll even put a line here between the two, just showing you that this stuff on the bottom here isn't quite as important, but it's a good time to talk about it while we're mentioning single, double, and triple bonds. Okay, but the important stuff here is on top of the line. When we have a carbon with 4 single bonds to it, this carbon is what we would consider sp3 hybridized, because we're hybridizing or mixing the s orbital and all the p orbitals to make 4 equivalent orbitals, which we call the sp3 orbitals. This is just a way to explain why, when we observe these 4 single bonds in carbon, why do they all look exactly the same if they're coming from different orbitals? So we explain this by saying, well, they must be coming from the same orbital, the sp3. The geometry of this, for the geometry, thinking back to last lecture, all we have to think about here, we could use the chart, in fact, the chart that I drew last class. If you have that written down, you could use that here. But when looking at the geometry, I just consider how many things is this connected to? We have 1, 2, 3, 4. This carbon is connected to 4 different things. So this is tetrahedral. Okay, anytime carbon has 4 single bonds like that, 4 bonds to it, it's going to be tetrahedral, and those bonds will be sp3 hybridized. All right, now looking at the carbon double bond with 2 single bonds, anytime you see a carbon with a double bond in it, this is a carbon that's sp2 hybridized. sp2 hybridized. So all those bonds in black are sp2, and then this pi bond, the extra bond we have, is the leftover p orbital, making an overlapping with some other orbital, some other pi orbital. Okay, so a carbon with a double bond is sp2 hybridized. It has 3 sp2 bonds, 1 p bond. And what is the shape of this? Well, it's a carbon connected to 3 different things. 1 over here on the right, 1 down here, and 1 up here. It's a carbon connected to 3 different things. So what's the shape we get if we connect an atom to 3 things with no lone pairs? It's trigonal planar. Trigonal planar. This is why a C double bond C is flat. It's flat. It has sp2 hybridization because it's a carbon connected to 3 different things. So what's the best way that 3 things can spread out from each other in 3 dimensions? Around a central point, they become coplanar, and then they spread out 120 degrees apart from each other. Okay? So that's trigonal planar geometry there. If we have C triple bond C, we have 2 pi bonds. We have 2 pi bonds. And we have sp hybridization. So we have a s orbital and we have a p orbital left over. So the bonds in black are sp bonds. The bonds in blue are pi bonds, overlapping p orbitals. And the geometry, if we have carbon connected to 2 things, 1 on the left, 1 on the right, the geometry is linear. Okay, linear. So while we have, single, double, triple bonds up, I'm also going to throw in just some information on these bonds. These aren't numbers you should memorize by any means, but we should just see a general trend here. Let's look at the bond length for each of these. I'm going to draw down the bond length for each one. We have 1.54, 1.34, and 1.20. These are measured in angstroms, very small unit of measure. You'll see it like this, a capital A with a little circle on top. Okay, so you don't have to memorize these numbers, but what we should gain from this information is that single bonds are longer than double bonds, which are longer than triple bonds. So triple bonds are short, single bonds are long. The bond energy, these are in kilojoules per mole. Single bonds, the energy required to break a single bond, 368 kilojoules per mole. For a double bond, almost twice as strong, 632 kilojoules per mole, which makes sense because now there's two bonds. And the triple bond, 820 kilojoules per mole. So the triple bond is stronger than the double bond, which is stronger than the single bond. Okay? So single bonds are long and weak. Triple bonds are short but strong. So here I've drawn three different molecules. I drew one with a Lewis structure on the left, and then the other two I drew with bond line structure. So we can continue practicing with bond line structure as well as hybridization. Okay, so let's start first with our Lewis structure on the left here, just so that we can clearly see each and every atom as we consider its hybridization. Up here I've color-coded. I'm going to draw the sp3 hybridized carbons as red, the sp2 hybridized carbons as green, and the sp hybridized carbons as blue. Okay. So looking at our structure on the left, so we're just considering each carbon atom. Let's start with the carbon on the left and just work our way down. Our first carbon has 1, 2, 3, 4 single bonds. So this carbon here would be sp3 hybridized, because remember, 4 single bonds is sp3 hybridized. All 4 of those bonds are equal and equivalent, sp3. The next carbon is double bonded to oxygen, and then it has 2 single bonds. So this carbon, if it's double bonded to oxygen, that means it has a double bond. That means it's sp2 hybridized. sp2. The next carbon is double bonded to another carbon and has 2 single bonds. So this carbon is also sp2 hybridized. And the final carbon, again with a double bond, is sp2 hybridized. Okay, so we have an sp3 carbon, and then we have 3 sp2 carbons. The sp2 hybridized carbons are flat with trigonal planar geometry, and this red carbon on the left is sp3 hybridized with tetrahedral geometry. So this right side of the molecule here, with all these double bonds, is a flat molecule. It's flat like a pancake. But then this red carbon on the left has some three-dimensionality to it. Okay, it has that tetrahedral geometry. So hopefully you can start to sort of picture the molecule in 3D as we work through these problems, as we work through the course. You'll start to be able to envision these molecules. And again, there's some really good software, ChemDraw 3D, a lot of other software where you can visualize, draw out these molecules, and see them three-dimensionally. Okay, so let's look at our next structure here, considering the hybridization of these carbons. Remember, wherever you see a vertex or some sort of end, there's a carbon atom. And then the extra bonds here, that's just the double bonds or the triple bonds, right? When we're considering where the carbons are in a bond line structure, we're just looking at the sigma bonds, at the main lines of the drawing. So in this case, we have 4 carbons connected in a square. This is a cyclobutane. If we have a double bond in here like we do, this would be a cyclobutene. Remember, ene, E-N-E, is the prefix for a double bond. So we have 4 carbons connected together. Let's start looking at the top left carbon. This top left carbon has how many implicit hydrogens? It has 1, 2 implicit hydrogens because it has 2 bonds to other carbons. 2 bonds are drawn. That means 2 bonds are undrawn. So we have 2 implicit hydrogens there. That's a CH2. That means we have sp3 hybridization if we have 4 single bonds. So that's an sp3 hybridized carbon. Let's look to the right, the top right. We have well, let's draw in how many implicit hydrogens do we have? We have 1, 2, 3 bonds, which means it has 1 implicit hydrogen. We have a double bond down, and then 2 single bonds. So this is going to be sp2 hybridized. Same for the carbon just below it. It has a double bond and then a single bond to carbon, also 1 implicit hydrogen. And then on the bottom left, we have another CH2 connected to 2 other carbons. That's 4 single bonds. So that is also an sp3 hybridized carbon. Okay. Now looking at our last example, we have a little bit more complicated structure here. We have a 5-membered ring with a triple bond coming off the bottom. Let's start on the top by the C double bond O. Okay. If we have carbon double bonded to oxygen with 2 bonds coming out away from it, that means it's sp2 hybridized, right? Carbon with a double bond and then 2 single bonds. Let's work our way all the way around the circle clockwise. The next carbon here is connected to 2 other carbons. So it's a CH2. It has all single bonds. So that's sp3 hybridized. Okay. Now let's draw out the implicit hydrogen for the next one because it might be confusing. This carbon here is connected to 1, 2, 3 other things, which means there's 1 hydrogen. So that's a CH connected to 3 other carbons. So this is still sp3. We're not at the triple bond yet, right? This is connected to a triple bond, but this carbon right here in red that I just drew, that's not a part of the triple bond. Don't let it confuse you. Let's continue around the circle. The next carbon has a double bond on it. And the next carbon also has a double bond on it. Okay, so hopefully now you can sort of start to see them faster. Single bond sp3, double bond sp2. Now let's work our way down this chain that has the triple bond on it. Let's draw any implicit hydrogens in. So at the end of this straight line here, we have this triple bond. Now the triple bond in bond line structure can confuse students a lot because you leave a little gap sometimes. You don't have to, you could connect them. But either way, it's confusing because remember, the triple bond is linear. So we draw them in a straight line. So what we have to consider here is that there is a carbon where I draw this bubble. There's a carbon there, right? There's a carbon, but we're drawing it in a straight line without a zigzag because the CC triple bond by nature is linear. It's a linear structure. Because of VSEPR theory, those substituents want to spread out as much as possible. If we only have 2 substituents, they'll spread out in a straight line. So don't let this confuse you. There's a carbon on the side. There's a carbon on this side. There's a carbon on both sides of that triple bond. So I think it's easiest to draw them in with little bubbles if you're confused. Boom, boom. So we have this red carbon, which is sp3 hybridized, connected to this black carbon here. That black carbon, what color should it be? It should be blue because it's part of the triple bond. It's the carbon that starts the triple bond. and then it goes over here to this other blue carbon. And that other blue carbon has 3 bonds. It's triple bonded, but there's also an implicit hydrogen, which we didn't draw right there in the end. Okay. There's an implicit hydrogen at the very end. So remember, all the carbons should have 4 bonds. Don't let that confuse you, and don't let those triple bonds in bond line structure confuse you either. But ultimately, hybridization is really not that bad. If you're just considering the geometry and the hybridization, all you have to do is look at the bonding pattern, figure out what hybridization you might have. And I think it's very important to also understand the geometry associated with it. We should be aware that these SPs are linear. We should be aware that these SP2s are trigonal planar and flat. And we should be aware that the SP3s are tetrahedral. I think that's important. The next lecture we do will be dealing with polarity and intermolecular forces. And then we will do our second workshop, covering everything from the first workshop up until next lecture. Okay? Okay, thanks for joining me today, and I will see you guys in the next one.